In this video, we are going to talk about matrices and linear transformations. This is our overview slide, which we'll spend about 5 minutes going over before we go over each topic in more detail and with more examples. We are going to start by looking at how to represent a linear map by a matrix. And to produce a matrix to represent a linear map, we're going to use the fact that once you know how a transformation acts on a basis for a vector space, you know how the transformation acts on all the vectors in the vector space. We'll look at matrices, and we'll see that an M by N matrix is a rectangular array of elements in F. It could be real or complex entries with M rows and N columns. The notation A sub jk denotes the entry in row J and column K of the matrix A. The matrix of a linear map T will denote that with M of T. So suppose T is a linear map from V to W, and V1, V2 up to Vn is a basis for V, and W1, W2 up to Wm is a basis for W. The matrix T with respect to these bases is the M by N matrix, M of T, whose entries A sub jk are defined by T V of k equals A sub 1k W1 plus A sub 2k W2 plus up to A sub mk Wm. And this is our first example of converting a linear map to a matrix, or finding the matrix to represent a linear map. We have this linear map F that maps from R2 to R3, a two-dimensional vector, to a three-dimensional vector. We find our bases for R2, or in this case, it's F2 because these can be complex numbers. So we find our bases for F2. We use the standard bases 1, 0, 0, 1, and we find our bases for F3 using the standard bases 1, 0, 0, 0, 1, 0, and 0, 0, 1. Then we take the transformation, our F, on our first basis vector, which is 1, 0, and we get the vector 1, 2, 7. And then we take the transformation of our second basis vector, which is 0, 1, and we see that we get the vector 3, 5, 9. So then our matrix representation of the transformation is the vector that the first basis vector is mapped to, that's 1, 2, 7, and the second vector is where the second basis vector is mapped to, 3, 5, 9. We will have more to say about this in the main part of our video. We will then define addition and scalar multiplication of matrices. We start with defining how to add two matrices, which at this point I'd be surprised if you haven't figured out how to do that. But we use this so we can go on and define the matrix of the sum of linear maps. So if S and T are linear maps from V to W, then the matrix representing the linear transformation S plus the linear transformation T is equal to the matrix representing transformation of S plus the matrix representing the transformation of T. Similarly, for scalar multiplication of a matrix, if this little alpha here is a scalar times A, then its coordinates, each coordinate then is multiplied by the scalar alpha. And we can use this then to define the matrix of a scalar times a linear map. So if alpha is a scalar and T is a linear map from V to W, then the matrix representing alpha times T is equal to alpha times the matrix times T. Also, just a note on notation, F raised to the mn for M and n positive integers is the set of all M by n matrices with entries in F. And the dimension of F of mn is equal to m times n. And finally, we will talk about matrix multiplication. And again, I think you've probably seen this by now. So A is an M by N matrix, and C is an N by P matrix. So AC is the M by P matrix, and remember, these two numbers, this N, needs to match this N here, and they sort of cancel out to give you an M by P matrix, where the entry in row J and column K is the dot product of row J of A and column K of C. And here's the formula. And a reminder that matrix multiplication is not commutative. We will illustrate that. And then we use this definition of matrix multiplication to talk about the matrix of the product of linear maps. So if T and S are linear maps, and T maps from U to V, and S maps from V to W, then the matrix that represents S times T is equal to the matrix of S times the matrix of T. And finally, we'll talk about linear combinations of columns, which we have been using. So if A is an M by N matrix and C is an M N by 1 matrix, so this should really be a column vector, then A times the vector C is equal to C1 times the first column of A plus C2 times the second column of A up to Cn times the nth column of A. In this way, we'll see A times C is a linear combination of the columns of A with scalar multipliers from our vector C. We will see, no pun intended, we will see an example of this. That wraps up our overview, so we can go back and start on representing linear maps with a matrix. We will start with the definition of a matrix. So an M by N matrix A is a rectangular array of elements of F, so either real numbers or complex numbers, with M rows. So you can see we have row 1, row 2, row 3, all the way up to row M, and N columns. So you can see we have column 1, column 2, column 3, all the way up to column N. The notation A sub jk denotes the entry in row J and column K of our matrix A. Our example is this matrix here. It's a 2 by 3. That is, it has 2 rows, 3 columns. And, you know, I just keep saying to myself row then column. It's always row then column. So 2 by 3, 2 rows, 3 columns. The entry A23, again, row, column. That's the second row. So we're in this row here. Third column, so that's this element here, 7. We are going to look at the matrix of a linear map. In other words, suppose T is a linear map from V to W, V1 to Vn is a basis for V, and W1 to W2 is a basis for W. We're going to then find the matrix to represent the linear map T, and we're going to use these bases, the V bases and the W bases, to form our matrix M of T. And if T is a linear map from Fn to Fm, unless stated otherwise, we're going to assume the bases in question are the standard bases. So here for your reference, I have the notes on the matrix of a linear map. And we are going to use this example that we saw in our overview slide, where the transformation is going from F2 to F3. In other words, a 2-dimensional vector, T of x, y, and that'll give us a 3-dimensional vector, which is x plus 3y, 2x plus 5y, and 7x plus 9y. I'm going to go ahead and write f in column form, so our f of xy is equal to x plus 3y, our second coordinate will be 2x plus 5y, and our third coordinate will be 7x plus 9y. And our bases for f2, this xy, is 1, 0, 0, 1, and our bases for f3 is 1, 0, 0, 0, 1, 0, and 0, 0, 1. You will not always have the luxury of being able to use the standard bases, because sometimes you'll be doing transformations to a subspace of F2 or F3, in which case your bases will look different. But when you go to the entire F2 or F3 or any f of n subspace or vector space, then you get to use the standard bases. Here, in our little overview here, the matrix T with respect to these bases is the M by N matrix, whose entries A sub jk are defined by T of vk. So here I'm going to start with T of v1, that is the transformation of my first vector, T of 1, 0. When I plug that in, I'm going to get 1 plus 3 times 0. Then I have 2 times 1 plus 5 times 0. And then 7 times 1 plus 9 times 0. So that gives me the vector 1, 2, 7. And there are a couple of things I want to point out about this 1, 2, 7. First, T of v over here, we can write this 1, 2, 7 as a linear combination of our vectors of W of our range space. So W1, W2, W3. You can see it's this coordinate, first coordinate times our first basis vector, second coordinate times our second basis vector, and third coordinate times our third basis vector. Now we can look at how we defined our matrix over here. We said T of v1, so k is equal to 1, which means A of 1, 1 times W1 plus A of 2, 1 times W2 up to A of 3, 1 times W3. So A11 W1 plus A21 W2 plus A31 W3. So if we look at this, this is W1. So A11 of our transformation matrix is going to be 1. A21, that's what multiplies W2. So 2 is going to be our A21. And then over here, multiplying our W3 is going to be 7. That's our A31 in our matrix. This actually, all of this work here kind of makes it seem more complicated than it is, but I did want to show you how to relate this formula to what we're going to do next. I do the same thing for TV2, so our second basis vector, I put it through the transformation, so x is equal to 0, y is equal to 1, so we have 0 plus 3y, 0 plus 3 times 1, 2 times 0 plus 5 times 1, and then 7 times 0 plus 9 times 1, so we get the vector 3, 5, 9. And again, we can write our vector 3, 5, 9 as a linear combination of our bases for w. So that's 3 times our first basis vector, 5 times our second basis vector, and 9 times our third basis vector. Now our matrix is going to be A11 is 1, A21 is 2, and A23 is 7. A12 is 3, A22 is this 5, and A32 is this 9. Or you can just simply look at this as the matrix is our first basis vector transformed, 1, 2, 7, and our second basis vector transformed, which is 3, 5, 9. I want to now use this matrix, so I'm going to shrink this down over here, and I'm going to put the matrix here, and I'm going to calculate my transformation on the vector 2, negative 1. Using this formula here, what I'm going to get is negative 1, negative 1, 5. But now I want to use my matrix to calculate the transformation. So I'm going to put my matrix 1, 2, 7, 3, 5, 9, and then put my vector 2, negative 1, and if you see, I'll get the same answer, negative 1, negative 1, 5. And if I write all the intermediates, of the scalar multiplication and everything, you can kind of see why they're going to give you the same answer. On our overview slide, I made the comment that we can use the fact that once you know how a transformation acts on a basis for a vector space, you know how the transformation acts on all vectors. So we can look at this example in light of this comment as well. So looking at f on the vector 2, negative 1, we can break 2, negative 1 as a linear combination of our basis vector. That's 2 times our first basis vector plus negative 1 times our second basis vector. And now using linearity and homogeneity, this gets converted to 2 times f of our first basis vector minus 1 times f of our second basis vector. So essentially, because we know how the transformation works on our basis vector, and any vector in the vector space can be written as a linear combination of our basis vector, we then use homogeneity and additivity to break it down till we eventually get 2 times whatever our first basis vector gets mapped to, which is the 1, 2, 7, minus 1 times whatever our second basis vector gets mapped to. That's the 3, 5, 9. It really is worth or being comfortable with these different representation of the same matrix transformation. Our next example goes from the polynomials of degree 3 or less to the space of polynomials of degree 2 or less. And our transformation is d, which represents the derivative function. So the derivative on p of x is equal to p prime of x. So we want to find the matrix representing the derivative function with respect to the standard bases. So our standard bases for polynomials of degree 3 or less are the bases with the number 1, x, x squared, and x to the third. The standard bases for polynomials of degree 2 or less are the vectors 1, x, and x squared. Now the next thing we need to do is apply the transformation on each of our bases vectors. So we need to apply the transformation on 1, x, x squared, and x cubed. So we'll start with 1. We want to take the derivative of the function 1, and the derivative 1 is 0. And writing that as a linear combination now of our bases in R2, that's going to be 0 times 1 plus 0 times x plus 0 times x squared. So in other words, it's the vector 0, 0, 0. Next, we're going to take our transformation on the vector x. So the derivative of x is equal to 1. In terms of our basis vectors for P2, that's going to be 1 times 1 plus 0 times x plus 0 times x squared. So it's the 1, 0, 0 vector. For the second basis vector, x squared, we take the derivative of x squared, we get 2x, which is equal to, in terms of our P2 bases, 0 times 1, 2 times x, and 0 times x squared, or the vector 0, 2, 0. And finally, we're going to take our last basis vector, x cubed. We take the derivative to get 3x squared, which in terms of our P2 vector space is 0 times 1, 0 times x, and 3 times x squared, or the 0, 0, 3 vector. This means our transformation matrix is equal to our first vector, 0, 0, 0, our second vector, 1, 0, 0, our third vector, 0, 2, 0, and then our last vector, 0, 0, 3. And we can test this out on a polynomial. Say my polynomial is equal to 6 plus 2x plus 0x squared plus 4x cubed. Our derivative then, this goes away, this goes to 2, this is 0, and this goes to 12x squared. So I can take my matrix 0, 0, 0, 1, 0, 0, 0, 2, 0, 0, 0, 3, multiply it times my vector representing this polynomial, which is 6, 2, 0, 4. And you see when you multiply this vector times the matrix times this vector, you're going to get the vector 2 plus 0x plus 12x squared, which is exactly the derivative we found using calculus. Now we are going to go to addition and scalar multiplication of matrices. We will start with addition of matrices. So when we add two matrices together, we essentially add corresponding elements of matrices. So for example, if this represents our matrix A, so it has columns A11, A21 up to AM1, A12, A22 up to AM2, all the way up to the column A1n, A2n up to AMN, and we add that to our C matrix, so that's the matrix with column vectors C11, C21 up to CM1, the next column C12, C22 up to CM2, and our final column C1n, C2n up to CMN. And one thing to note, to add matrices, they need to be the same size. So over here, that's sort of indicated that the J and K, the number of elements need to be the same. But you essentially add the corresponding elements. So A11 gets added to C11 to make the 1, 1 element of our A plus C matrix. A12 gets mapped to A to plus C12 is our next element. And then over here, A1n gets added to C1n. Going down now the column, so A21 plus C21 is over here, A22 plus C22 is here, A2n, C2n is here, and then the final row, AM1 plus CM1 is our first entry in the final row, AM2 plus CM2 is our next entry, and our final entry is AMN plus CMN over here. When we multiply a scalar times a matrix, we essentially just multiply every entry by the scalar. So alpha, if this is a scalar, times our matrix A is equal to, now every entry, A11, A21, AM1, they're all multiplied by our scalar alpha. Our next column, every entry, A12, A22 up to AM2 is multiplied by a scalar alpha. Now to look at matrix multiplication, to get the entry of row J and column K, that's the dot product of row J and the column K. So let's look at this. If this is our matrix A, and let's say it's 3 by 2. And this is our matrix C, and it's 2 by 4. So the first thing you want to know is for matrix multiplication to be defined, these two numbers need to be the same. So up here, this n needs to be the same as this n for A and C. So the number of, this is row columns, the number of columns in your first matrix must equal the number of rows in your second matrix in order for matrix multiplication to be defined. And then The other thing that's kind of nice is I like to think of these two canceling out, so our resulting matrix is going to be 3 by 4. So let's start by doing the multiplication. Again, it's the row dotted with the column. So row 1 dotted with column 1 gives us our entry for A11. So it's going to be 1 times 6 plus 2 times 2. That's our first entry. Now for our first row, second column, A12 entry, that's going to be the first row times the second column. So 1 times 5 plus 2 times 1. And then we have 1 times 4 plus 2 times 0. And 1 times 3 times 2 minus 1. That's this row. For our second row, so for element, and it's row column, so 2, row 2, column 1, we're going to take row 2 here, multiplied by column 1. So that's 3 times 6 plus 2 times 4. And then for the 2, 2 here, we're going to do the second row, second column, 3 times 5 times 4 plus 1, 3 times 4, 4 times 0, and then 3 times 3, 4 times minus 1. And then for the third element, row 3, column 1, it's always row first, row 3, column 1, we're going to take row 3, column 1, 5 times 6, 6 plus 6 times 2. For row 3, column 2, it's row 3, column 2, 5 times 5 plus 6 times 1, 5 times 4 plus 6 times 0, 5 times 3 plus 6 times minus 1. So our final matrix is going to be the matrix with column vectors 10, 26, 42, 7, 19, 31, 4, 12, 20, and 1, 5, 9. And a reminder to you, matrix multiplication is not commutative. If I try to multiply this 2 by 4 matrix by this 3 by 2 matrix, you can see they don't have the right sizes. And so in this case, I can't even do the row this times column this because I don't have enough. I need another element here to multiply by 3. So my matrix multiplication is undefined. And so in this case, our A times C is not equal to C times A. And even if it were defined, you might get a matrix. You might be able to multiply it, but the ending matrix, the resulting matrix, may or may not be equal to, but you're not guaranteed that it'll be equal to A times C. And now we can look at the matrix of the product of linear maps. So if S and T are linear maps, T goes from U to V, and S goes from V to W, then M of S times T is equal to M of S times M of T. And this is almost like function composition. I have a couple more examples to give you. The first one is this matrix 3, 4 times the matrix 6, 2. And you'll notice the 3, 4 is a 1 by 2 matrix, right? 1 row, 2 columns. And here we have a 2 by 1 matrix, 2 rows, 1 column. You can see these match, and we're expecting a 1 by 1. In other words, we're expecting a scalar. So we have this row times this column. We have 6 times 3 plus 4 times 2. So that gives us the scalar 26. For our next example, we have this 3 by 2 matrix with column vectors 1, 3, 5, 2, 4, 6, and this column vector with entries 5, 1. So now we're going to multiply the first row times the column. We get 1 times 5 plus 2 times 1. We get 3 times 5 times 4 plus 1. And then 5 times 5 plus 6 times 1. So our final answer is the vector 7, 19, 31. And just to verify we have the right dimensions, this is 3 by 2, this is 2 by 1. So we're expecting a 3 by 1, 3 rows, 1 column, and that's exactly what we got. Our next topic is about linear combinations of columns. So if A is an m by n matrix and C is an n by 1 matrix, then A times C is equal to C1 times the first column of A plus C2 times the second column of A up to Cn times the nth column of A. That is, AC is a linear combinations of the columns of A with scalar multipliers coming from C. And just to go over this notation where there's this dot, the dot means that represents all the possible values where the second, the number is held constant. So in this case, the dot is in the row position. So that means this is all the possible entries of the row, but we're on the second column. So the dot, comma, K denotes the kth column of A. Whereas if the dot is in the row position, that means we're in the jth row of A, and the dot represents all the other elements where J is fixed. And the example of this notation using this matrix here with columns 8, 1, 4, 9, and 5, 7, then A2 dot, in here the row is 2 and the column varies. So row 2 is the 1, 9, 7, where the column varies 1, 2, and 3. So that's row 2 of A, which is 1, 9, 7. The A dot 2, so the row varies and the column is held fixed at 2. So the column's held fixed at 2 and the row goes from row 1 to 2. So that's this column vector here at 4, 9. So now we can continue on with our linear combination of columns example. We have our matrix A, which is the matrix with column vectors 1, 3, 5, and 2, 4, 6, and our column vector C, which has entries C1 and C2. So A times C then, A is a 3 by 2, C is a 2 by 1, so we're expecting a 3 by 1 at the end. But if we look at this, we're going to have our row times column, so 1C1 plus 2C2, 3C1 plus 4C2, 5C1 plus 6C2. So in other words, you can look at this as one group of vectors here that gets multiplied by C1, and another vector here that gets multiplied by C2. So in other words, we have the vector 1, 3, 5 multiplied by C1 plus the vector 2, 4, 6 multiplied by C2. And you can see then a matrix times this column vector, where the column vector only has one column, is essentially a linear combination of each of the columns of A. So the first column vector is 1, 3, 5 times C1 plus the second column vector times C2. So we use this a lot previously in other videos when we're doing row reduction and looking and determining if things were linearly dependent or independent, but this is kind of the formal reason why this works out. I'm going to move this example up so I can do one actually where my C vector is not just constants but actually numbers. So let's take our same matrix A, 1, 3, 5, 2, 4, 6, and our C vector now to be 5, 1. So you can do the matrix multiplication out, but you can also know that this can be viewed as our 1, 3, 5 times our 5 scalar and our 2, 4, 6 vector times our 1 scalar. To review what we covered in this video, we talked about matrices and linear transformations. We started with talking about representing a linear map by a matrix, and to produce a matrix to represent a linear map, we used the fact that once you know how a transformation acts on a basis for a vector space, you know how the transformation acts on all vectors in the vector space. We looked at a matrix, which is an m by n matrix, is a rectangular array of elements of F, being either real numbers or complex numbers, with m rows and n columns. The notation A sub jk denotes the entry in row j and column k of the matrix A. We can have a matrix to represent a linear map. So we said M of t is the matrix. We said suppose T is a linear map from V to W, and V1, V2 up to Vn is a basis for V, and then W1, W2, Wm is a basis for W. Then the matrix of T with respect to these bases is the M by N matrix whose entries A sub jk are defined by T of Vk is equal to linear combinations of the matrix columns times the bases of W. Our example was this transformation from F2 to F3. So it's defined by taking a two-dimensional vector to a three-dimensional vector such that f of xy is equal to x plus 3y, 2x plus 5y, and 7x plus 9y. So what we did to find the matrix to represent this is we first transformed our first basis vector from F2, that's 1, 0, and we saw it transform to 1, 2, 7. We transformed the second basis vector over here from our transformation, and we saw that the transformation on 0, 1 was equal to, over here, 3, 5, 9, which then means the matrix to represent this transformation is the transformation of our first basis vector, and the transformation mapped it to 1, 2, 7, and then the transformation of our second basis vector, which was mapped to 3, 5, 9. We talked about the sum of two matrices, and the two matrices need to be the same size, and that's just equal to the sum of the corresponding entries, so that we could define then the matrix of the sum of linear maps. So if S and T are linear maps from V to W, then the matrix to represent S plus T is the matrix of S plus the matrix of T. We defined a scalar times a matrix, so a scalar times a matrix A just multiplies each element of A by this scalar, which means when we have linear maps, a scalar times the linear map is equal to the matrix representation is the scalar times the matrix representation of our transformation. We also had this notation, f of m comma n, for m and n positive integers. That's the set of all m by n matrices with entries in f. No surprise, this is a vector space, and the dimension of f of mn is equal to m times n. Finally, we have matrix multiplication. So if A is an m by n matrix and C is an n by p matrix, and for multiplication to work, these two numbers need to be the same. So the number of columns in A needs to equal to the number of rows in C. So we can define then A times C is the m by p matrix, where the entry in row J and column K is the dot product of row J of A and column K of C, and this is our formula. We did some examples of that, and we also re-emphasized that matrix multiplication is not commutative. We also looked then at the matrix of a product of linear maps. So if S and T are linear maps, and T goes from U to V, and S goes from V to W, and again, the idea is this range is equal to this domain in the same way that this number of columns has to equal to the row. So this must go from T to V, and this goes from V to W. Then M of S times T is equal to the matrix of S times the matrix of T. And finally, we said that we can view linear combination of columns. So if A is a matrix, m by n, and C is an n by 1 matrix, then A times C can be viewed as a linear combination of the column vectors of A, with the scalar multipliers coming from C. And that's it for this video. Thank you for watching.